Welcome back to Teaching the Unteachables, where we dive into teaching and learning methodologies for professionals like you. This episode is part of episode 74 of Did You Know the ESCO HVAC Show. Learn more about Regal Rexnord at regalrexnord.com.
All right, so this is where we left off in the history lesson. We took a side, the off ramp to PSC motors for a little bit, but we left off 1986 saying that back then all indoor blower motors were using PSC technology. So if we fast forward to 2005, and it'll become clear in a few minutes, like why did he? That's a very obscure year to jump to, but it'll make sense. There's always a method to the madness. I need to borrow your Einstein hair when I say that. So ECMs were introduced in 1987. That's why I chose 1986 as the starting point, because the very next year we started introducing ECM technology. So if you fast forward to 2005, which if my math is correct is about 18 years later, we see that in the indoor blower motor market of brand new equipment, that ECMs had gained about 15% of the market share. And I don't know about any one of you that may or may not, do investments or focus on investments or investment in manufacturing companies, but that's not a good business model to penetrate only 15% of the industry in 18 years. But there's a very good reason why, and I'm going to explain that in just a minute. So 18 years later, 2005, we've got ECMs in the industry. We've gone through multiple iterations in that time frame. Anybody that's been around long enough remembers the old square back one. Oh boy! And then we progressed to the one with no paint on it that looked kind of weird, and then the 2.3, which is the name of this motor that went from 98 all the way to 2013. So whether it's air handler package or fossil fuel, again, only about 15% of units were using ECM. So before I tell you why only 15% of the industry had switched to that technology, let's take another detour and talk about what is ECM, because we've done 3 discussions so far on each one of the ECM technologies, and we've drilled down, explained the nuts and bolts of how they work, the diagnostics, the airflow, but we've really never explained the technology itself, the what's going on the inside. So ECM, of course, stands for electronically commutated motor. If you're one of those typo experts, you don't like to type ECM or electronically commutated motor. So, it's really EC motor.
It's just ECM. Or EC motor. Yes.
Well, and I have to say that because very recently there was I think it was a manufacturer, it may have been another training organization, but they were calling all their motors EC motors. And I started getting these phone calls. I say, hey, are these EC motors brand new? Or are they just like yours? Like, it's an ECM. Yeah. You're on the phone, you could just hear them turning red. Like, I should have known that. Gosh, okay, I'm all good. Never mind.
Motor, Chris.
Right. Motor. But we have these other terms that also get used, and the brushless DC and permanent magnet. And the thing is these terms are a part of the technology of the motor. So an ECM, technically, I'm going to read this verbatim. It's a brushless DC 3-phase motor with a permanent magnet rotor. The motor phases are sequentially energized by electronic control, powered from a single-phase power supply. Probably could have read it without staring at the screen, but I like to get that one exactly right because it was written by one of my engineers, and
there you go.
I want to plagiarize properly. So, but we end up with these terms. What is permanent magnet motor, PMM? What is BPM, brushless permanent magnet, BLDC? What do these all mean? Well, basically, to understand that, you have to understand everything that's going on inside of an ECM, because these terms are bits and pieces of the technology. So in an ECM motor, in the control, so you see here I've taken the control off of the motor. So here's the motor. I know you can still see me on the little screen there. Yep. And here's the control. Yep. I know you can see it on the screen, but I wanted to pop it up. So the so I'm at the point where I've got AC power coming in. I'm converting that AC power to DC power, and now I have a clean DC power source inside my ECM control. Okay, good to go. Yep. That volts DC power is going to power my microprocessor, just like it does in your home computer, your laptop, your phone, anything you're using. But that DC power is also going to go through my frequency drive, and it's going to operate the motor. So going to the motor, and this is where this is where in many classes I'll finish this sentence or this phrase and I'll pause and I can see a little bit of smoke coming out of ears.
Yeah.
Right. So
this is
so what is actually going to the motor? Is it DC power or is it AC power? Well, on an oscilloscope, it would look like an AC sine wave. It looked like a 3-phase AC sine wave. But if you look a little closer, you're going to see ripples in the flat areas of that sine wave. And what those ripples are is that is not actually a clean sine wave. It is a PWM frequency drive that's turning the power on and off. So it turns it on and off from 0 to positive voltage, on and off from 0 to negative voltage over a proper amount of timing, and it ends up looking like an AC sine wave. And you might think, well, boy, that would have to be going on and off really fast, and it is. It's around 20 kilohertz, which is 20,000 times per second, right? So my analogy, because I like analogies, they help people remember things and relate. So the lights in most of your rooms are probably fluorescent lights, and they're running off of ballasts, and they're actually turning on and off because they're running at a certain frequency. But my light doesn't. This isn't this isn't the 70s. This isn't a strobe light. I'm not doing but yet this light is actually turning on and off so quickly. It just looks like continuous light. And so that's what's happening in an ECM motor. I am truly sending DC power to that motor winding, but that DC power is being pulsed on and off at proper intervals so fast, it just looks like a 3-phase sine wave going to the motor. And I put these two up here, and I didn't want to get too nerdy in here, and I didn't want us to be here till like 10 o'clock at night. But yeah, well, we've already gone down the rabbit hole. Now we're going into the rabbit hole cave. So if you look at this sine wave, in the early years of ECM technology, this was called sort of a trap drive, a trap wave, trapezoidal looking waveform. And so technicians would often ask in the early years, why does the motor kind of rock, and then take off? And so again, if you think about this technology came out in in 87, do you remember how powerful Windows 95 was and how slow it was?
Right.
So think about that era processor being in this motor and having the responsibility for directing the frequency drive to do all this work. So it didn't do it very fast. It had to get rotor positioning back from the motor to know that it was starting the motor in the right direction. And so all this took a couple of seconds to happen. So in the early ECM technology, the motor would and then take off.
Yeah.
But if you've ever paid attention to an ECM from the last 10 years or even 5 years, they just seem to take off. There's really no rock. If they do rock, it's so slight. You got to be like, I'm gonna catch it. I'm gonna catch it. And it barely moves. Well, that's because now we have what's called the sine wave drive. And the sine wave drive creates a sine wave that actually looks almost exactly like a true waveform, still being pulsed. But now that I've got a more powerful microprocessor, I can create that wave. I can stitch that wave together more cleanly, and I get less of that starting fluctuation.
Man, now we're getting into the nuts and bolts. This is what we teach in class, right? That's the whole point of diving into what are we looking at? How do we teach this in our class? How do we make this more comfortable? And so it's important to understand what that control is doing, what our motor is doing, how it's constructed. I think this is a good time. I want to introduce another perspective for us to have in the classroom. When we're talking about ECM motors, so if we take the control off from that motor, Chris, we're stuck with a 3-phase motor that has a rotor inside, and we have our stator on the outside in a 3-phase position. Now, I want you to think about this for a minute, because I get this question fairly often. Are there ways that we can show the motor in an electrical way that makes sense for technicians? Can we use it for different purposes? I do this in classroom, and I've resurrected one of my old training projects to be able to show that 3-phase motor is really an interesting component that we can use for other purposes. Now, we've talked a lot about the construction of it, and I want people to pay attention. See if you catch the terminology that could be construed a little bit off, but is kind of right. So I want you to think about it. Yes. So I need to do a little adapting to it, but I threw this together just for our educators to be able to put motors into a perspective that is a little bit more hands-on. So, are we ready? Huh?
Roll that beautiful bean footage.
Here we go. So when we talked about the induction side of a motor, Chris, what we were truly talking about was a slightly different style of motor. So I really need to reframe that a little bit and talk about the motor. So let's look at what induction really would look like.
So I took this motor apart, and this is obviously an ECM, but if this were a PSC motor, the rotor would be made of aluminum bars, and I would still basically have the same stator. I'd still basically have steel with copper wrapped around the laminations. And so in a PSC motor, this rotor would have no magnetic effect when there's no power to it. But when I put energy to the stator and I start creating a magnetic field around this stator, that magnetic field is going to induce a magnetic effect into the rotor. And that's actually where the term induction motors comes from. Right. That rotor doesn't have any magnetic effect and can't follow the rotating magnetic fields until the rotating magnetic fields establish themselves, induce some of that magnetic effect into the motor. It's also why the PSC motor is less efficient than the ECM. It doesn't have near as much to do with the electronic control, the electrical efficiency. Doesn't have near as much to do with the electronic control module as it has to do with the permanent magnet rotor inside the ECM. So when you add a permanent magnet rotor to so this is a three-phase motor. No qualms about that. Question is, and this is a question of maybe, engineer speak versus technician speak.
This is deeper than me.
Is it an induction ECM motor? Is it an AC ECM motor? Or is it a DC or three-phase motor? Is it a induction, AC, or DC three-phase motor? Well, I've got a permanent magnet rotor in the middle. Okay, so I don't need to induce a magnetic effect from the stator into the rotor to generate that magnetic effect. It's already there. So it really is somewhat improper to call it an induction motor. But if you're teaching this to a technician who's not an engineer and just needs the concept of, oh, that's just a basic three-phase motor, then calling it a three-phase induction motor helps them understand, it's going to have three windings. Those three windings, if they're working properly, should all ohm out with the same ohms. I reverse any two phases, the motor will change direction. So I think it's okay at a high level. Well, when I'm teaching contractors and technicians, it's a three-phase AC induction motor, because they're going to get that impression of how they would diagnose it, and that's perfectly fine. At the technical level, it's really just a three-phase DC motor, or to what was used earlier, a three-phase brushless DC motor. So, and when I bring that up, I'm sorry, the kid in me always wants to go back to my Tyco race car sets, right? The little Tyco cars, those little rotors were little magnets, and when the car was completely destroyed, you'd tear it apart and you'd throw the magnet at things, see what it would stick to.
Absolutely.
And then when the car would slow down, you'd go to the hobby store and you'd buy new brushes. And what did the brushes do? The brushes flipped the polarity so that the magnetic field kept going back and forth and made the rotor go around. So that's where these terms come from, brushless DC. Is it a DC motor? Well, technically, yes, because the power being sent to the motor is DC. It's not AC, but it looks like AC to the motor, and we generate the same alternating current in the winding that causes the rotor to follow. We just don't need to induce that current into the rotor to create the magnetic effect. So a couple of things happen from that permanent magnet rotor. We get not only better efficiency, but we also get a smaller stator. And you look at the size of this, I probably should have a measuring stick out, but from here to here, from vent to vent, that's about 1.5 inches. That is the stator stack of a 0.5 horsepower ECM motor.
Sure.
If that was a PSC motor, that stator stack would be easily an inch longer.
Yep.
So how is an ECM stator that's shorter, less copper, able to still create a 0.5 horsepower of torque? It's because in a PSC motor, I'm wasting a certain amount of energy magnetizing that rotor, so I need that bigger stator to create the same amount of torque. With the permanent magnet rotor, I've already got all that energy that I would have had to induce. I've already got all that energy in the magnet. I don't have to use that energy in the to create the magnetic effect. Therefore, my stator becomes even more powerful in a smaller size. So a couple of things happen from the permanent magnet. We get better efficiency, and we also get a smaller profile of the stator stack of the motor. One more point of discussion before we leave this particular rabbit hole. I feel like there's more to come.
It might be a 5th month, Chris.
Those wascally webbits.
Right.
So on the left, you see what the early rotors looked like in ECM motors, and they were using what was called iron ferrite. So they're roughly a 1/4 inch thick. I believe this one is an iron ferrite. Yep, I'll hold that one up to the camera if you want to see it. So it's about a 1/4 of an inch thick, and you can see it's actually this one's actually in 3 segments. You can kind of see it there. The segment goes from here to here, and then the next segment goes to here. You can kind of see that little dimple there, and then comes around to here. So 3 individual pieces of iron ferrite. But as technology progressed, we started using neodymium. And neodymium, I'm going to throw a number out. It's probably not right, but I'm going to use it. It's 10%, 20%, 30% stronger than iron ferrite. So what happens is I end up with a much smaller magnet, which means my rotor profile changes. Because that neodymium is actually stronger than iron ferrite, you may have noticed in the last 5 to 10 years, ECM motors, the stator stack have even gotten smaller. And the reason they've gotten smaller is, again, because the rotor field has been made stronger with the neodymium magnets. So that's just a little bit more information about the rotor that won't help you diagnose the motor or set your airflow.
Well, it sure makes sense.
But it's a lot of fun when you know how the toaster works without having to take the whole thing apart.
Absolutely.
So we're going to apply that to the constant airflow motor. That was the technology that was introduced back in 1987, constant airflow. We left off at 2005. About 15% of the industry had started using constant airflow motors, but over 18 years, wow, that's a long time. You'd think that it would have had more of an impact on the industry, but it makes a lot of sense when you understand that constant airflow motors are only used in premium tier systems. So, two-stage heat, two-stage cool systems started in the late 80s, same time these motors were introduced. And so this motor, the constant airflow premium level motor, was only used in premium level systems. So if you think about that pie chart again, 85% still PSC, 15% premium level ECM, that kind of agrees with the way most contractors sell equipment, right? About 15%, depending on the market or region you're in, 15% is your premium level systems, and the other 85% is probably a mix of your mid-tier and your builder's grade level equipment. And when I'm in front of most contractors, like, it's pretty much, how, other than the rare contractor that sells a lot of premium or no premium, it pretty much washes out with the industry. So it makes sense why that motor, it's kind of like, we kind of launched, I like to use goofy analogies. It's kind of like we kind of launched like Tesla, right? We came out with our $80,000 car first, and then later came out with the affordable $35,000 car.
Here's option B.
Right. Here's option B for the masses,
the
right?
industry like we wanted it to.
Exactly. Then, and I don't think I've mentioned this yet. So ECM motors as a whole, and they can be a little higher or a little lower. As a whole, an ECM motors around indoor blower motor, outdoor fan motor, 48 frame, 1 horsepower and below. I don't want anybody, I know my motor's 89. So they're roughly 80% efficient. They can be as much as 85, and they may fall a little bit below 80% depending on where they're operating, but they're about 80% efficient. If you remember, I said that PSC motors are between 60 and 70, depending on where they're operating. If they're operating at lower speeds, they could be operating as low as 50 or 40% efficient. So we're anywhere from 10 to 50% more efficient than the PSC motor, depending on where we're operating it. And again, keep in mind, this motor was primarily applied to premium level two-stage systems. So it's going to spend a lot of time operating at the lower speeds because two-stage systems spend a lot of time operating in their first stage capacity. Yep. And then, we talked about this in episode 1. These are communicative motors. If you want to know more about that, go back to episode 1, and then you can get all that information. We're in high level mode here, so we're not drilling down there. These motors, again, often referred to as variable speed, and they're made in 2 very common styles. And I say 2, we make them. Right. We, Gentech, the formerly branded GE motors, make them in 2 styles. One with a 5-pin line voltage and the 16-pin communication, and one with the 5-pin line voltage and the 4-pin communication. One of our largest competitors makes the motor similar to the 5-pin, 4-pin, and then some of our other competitors make either different size pins or they use just all wires. But almost all of them are using either PWM or serial communication. Yeah. So, and the only reason I say that is you go back and watch episode 1, you're not going to just learn about Gentech motors. You're going to learn technology that'll apply to multiple brands of motor technologies.
Indeed.
So here's where it gets really interesting. Besides the electrical efficiency and this weird thing called a permanent magnet rotor, these motors by program can have an operating range of 300 to 1500 RPM.
That's pretty crazy.
So that's like going from an 8-pole motor, or even if there is such a thing as a 10, 12, there's a 12-pole motor, all the way up to a 6-pole motor, all in one motor. And the manufacturer of the appliance doesn't have to buy 10 different motors. They can program that motor as it's coming down the line. In this system, I need between 600 and 800 RPMs for my 2-stage system. In the next system, I need between 800 and 1,000. In my next one, they can program that motor for multiple systems without having to buy individual SKU ratings for each wired and wound motor. Highly sought after for those premium level systems, very versatile for the manufacturer. Also opened up the manufacturer to create airflow points that just were not possible with PSC motors. I don't know if we talked about it in any of our episodes, but the MERV rating has come up after COVID, MERV 13. Running your fan continuously, and running your fan continuously is very valuable for many reasons. But if you've got a PSC motor, it's going to cost you quite a bit of money. In an ECM, I'm actually running 50% or more efficient than a PSC motor when I'm running at 600 or less RPMs. And this ECM, for example, is going to run 600 or less RPMs, still around 80% efficient.
Wow.
So that's pretty huge when it came to IAQ.
Yeah, indeed. Man, we have some fun. All right, everyone. I know it's been a long evening. I'm so grateful that you hung out with us. All of these presentations are available for you on YouTube, where you can go into our e-learning network at the HVACR Learning Network, and you can actually get credit for these courses if you're looking for that for continuing education. So check that out. We'll see you all at the conference. Everyone have a wonderful evening, and we will see you next week on Did You Know, the ESCO HVAC Show.
What a great time.